Hi, in this video we are going to continue our course on polynomials and we are going to look at part 2 of our complex numbers section. So we start off with this problem. This is a question from China's team selection test 2004. It says let C1, C2 to Cn be real numbers and let g of theta be C1 cos theta plus C2 cos 2 theta and so on Cn cos n theta. Now, the question is saying that if g of theta is greater than -1 for all positive theta, we have to prove that C1 plus C2 plus Cn is less than or equal to n. So this is the condition of the problem. G of theta is greater than -1 for all positive theta. And then we have to prove this statement. So this is a question where you will learn how to apply the concept of roots of unity of a complex number. So let's look at that. I'll work it on out in the next screen. So let's say let z be equal to cos of 2 pi by 2n plus 1 plus I sine 2 pi by 2n plus 1. If you take z like this, then it is obvious that z power 2n plus 1 by De Moivre's theorem is cos 2 pi plus I sine 2 pi, which is equal to 1. So basically what we are getting, okay, we should not take 2n plus 1 here. We can take n plus 1 because the question is only going till n, Cn, right? So I'll take n plus 1 here and n plus 1 here. And I'm getting z power n plus 1 is 1, right? So z power n plus 1 is 1 means z power n plus 1 minus 1 is equal to 0. And this we can factorize as z minus 1 z power n plus z power n minus 1 plus z power n minus 2 till z plus 1 equal to 0. And since z is a complex number like this, clearly z is not equal to 1. Therefore, what we get is z power n plus z power n minus 1 and so on plus z plus 1 is equal to 0. This is a result that we have gotten if we took z as the n plus 1th root of 1. Right? If z is equal to this, then this result is true. Right? Now, let's try to use that identity by taking different values of theta. So what we can say is we needed something like this. G of theta was equal to C1 cos theta plus C2 cos 2 theta and Cn cos n theta, right? This is the function that we wanted to understand. And what we can say is if theta 1 is equal to 2 pi by n plus 1 and theta 2 is equal to 4 pi by n plus 1 and so on, theta n is equal to 2n pi by n plus 1, right? Then in those cases, theta 1, theta 2, if you keep putting it in this relation, you get g of theta 1 would be C1 cos 2 pi by n plus 1 plus C2 cos, you get 2 theta 1, so that is 4 pi by n plus 1, and you get finally Cn cos 2n pi by n plus 1, right? G theta 1 is this. Now, if you think about this, this is basically cos 2 pi by n plus 1 is what? Cos 2 pi plus n plus 1 is C1 into real part of Z, right? This is C2 into real part of Z square. Think about it. If you do Z square, you will get cos 4 pi by n plus 1. So that is the real part of Z square. And so on, you have Cn into cos of 2n pi by n plus 1, that is real part of Z power n. So now if you write this like this, the C1 and C2 and all are all real numbers. So we can say it is real part of C1Z plus C2Z square plus Cn Z power n, right? So that is what we have. We have G of theta 1 is equal to real part of this. Similarly, G of theta 2 let's take theta 2 as 4 pi by n plus 1, right? You will realize when you take theta 2 as 4 pi by n plus 1 and do the same expression, find out what is g of theta. So g of theta 2 is equal to c1 cos 4 pi by n plus 1 plus c2 cos 8 pi by n plus 1 and so on. So you will write this as c1 real part of z square plus c2 real part of z power 4, right? And so on. So this becomes real part of c1 z square plus c2 z power 4 and so on, right? This is g of theta 2, correct? Now, in the problem, they have said that g of theta is always greater than -1 for all positive theta, right? So what we know, I'll write on the next screen. So far, what we have figured out is g of theta 1 is equal to real part of c1z plus c2z square and cn z power n. And we know that it is greater than equal to -1, right? Greater than equal to -1, that was given in the problem itself, right? Now, similarly, g of theta 2 is equal to real part of c1 z square plus c2 z power 4 plus cn z power 2n. That is also greater than equal to -1. And similarly, g of theta n would have been real part of c1 z power n plus c2 z power 2n and so on till cn z power n into n, so n square is greater than -1. If you add all of this, if you add up vertically all of this, you get g of theta 1 plus g of theta 2 till g of theta n is equal to real part of, think about adding all of this. This will be c1 common z plus z square plus z power n. Then you can take c2 common and you get z square and so on, right? You can take c2 z common. Okay, we'll just take c2 common. You get z square plus z power 4 plus z power 2n. Then lastly, you take cn common. You get z power n plus z power 2n plus z power n square. The whole thing is greater than equal to -n, right? Now imagine we have already found that z power n plus z power n minus 1 till z plus 1 is equal to 0. We already found this earlier because z was equal to cos of 2 pi by n plus 1 plus I sine 2 pi by n plus 1, right? So what this means is that z power n plus z power n minus 1 till z is equal to -1, right? So if you think here, this is equal to -1, correct? And if you think here, this you can take z square plus z power 4 plus, okay. So this basically becomes we already know that z power n plus 1 is equal to 1. So here you are crossing over beyond z power n plus 1. Right? You are getting z square, z4, all the even numbers. And then after n plus 1, what will you get? So z square plus z power 4 plus z power 6, z power n plus 1 plus z power n plus 2. So notice that z power n plus 2 will be z, and z power 2n would be z power 2n minus n minus 1, so n minus 1. So all the numbers after this point are the odd powers, if you realize. This is becoming our 1. And when you go from z square, z power 4, z power 6. Notice this is z. So this is z plus z square and all. So you can easily prove that this is also equal to minus 1 because of these two results. Because z power n till z, the sum of first n powers of z is equal to minus 1 and z power n plus 1 is 1. You can prove that this part is also minus 1, this part is also minus 1. You should try it out yourself for any value of n. And therefore, what we can get is minus 1 common. You get real part of minus 1 c1 plus c2 plus cn is greater than equal to minus n, because this minus 1 was what? It was 1 plus, it was z power 1 plus z square till z power n. That is what is coming common. You can prove that this is the same thing as other versions of it. So z square plus z power 4 plus z power 6 till z power 2n is also the same thing as this, because z power n plus 1 is 1 and z plus z square plus z power n minus 1 is equal to minus 1. Because of these two results, this will match this. So you can take minus 1 common throughout and you get basically real part of minus 1 into this, and this number is itself a real number because the question had said that all the c's were real. So that is same as minus 1 c1 plus c2 plus cn is greater than equal to minus n, and you get c1 plus c2 plus cn is less than equal to n. When you divide by minus 1, the inequality sign changes, and which is what we wanted to prove. Now, what have we done in the problem? We took z as cos 2 pi by n plus 1 plus I sin 2 pi by n plus 1. We realized that z power n plus 1 is 1. We put different angles theta 1, theta 2 as 2 pi by n plus 1, 4 pi by n plus 1, 6 pi by n plus 1 and so on in the version of g of theta. And g of theta, we wrote it as a real part of c1z plus c2z square and so on. We added vertically. The question itself had told us that each of the g of theta is greater than equal to minus 1. We added vertically and used the inequality to realize that it works out. We are able to prove the statement. Let's see another problem. Again, we'll employ concepts of complex numbers here. Let's see what the question says. Let z be a complex number such that mod of z plus 1 is greater than 2. Prove that mod of z cube plus 1 is also greater than 1. This is the question. So let's think about what we can do here. Now, mod of z cube plus 1 using algebraic identities, I can write it as z plus 1 times z square minus z plus 1, right? Now, this means that this is greater than 2 times z square, because mod of z plus 1 is greater than 2. We can write it as greater than 2 times z square minus z plus 1, right? So we have an inequality right now. We have that mod of z cube plus 1 is greater than twice of z square minus z plus 1. If we are able to show, if we can show that mod of z square minus z plus 1 is greater than half, then we will prove that mod of z cube plus 1 is greater than 1 from here, right? So our job is to try to prove this statement, correct? Now, how do I do that? What I can say is, let's take the Euler form of a complex number or polar form of a complex number and say z plus 1, let's say, is r cos alpha plus I sin alpha, right? Let's say z plus 1 is this, where r is greater than 2, because the question has said that mod of z plus 1 is greater than 2, right? If z plus 1 is this, we will write our expression z square minus z plus 1 in terms of r and alpha. How do I do that? So let's see here. Z square minus Z plus 1 can be written as Z plus 1 whole square, which would be Z square plus 2Z plus 1. So I have to subtract minus 3Z. So minus 3 times Z plus 1 becomes minus 3 and plus 3. Right? What I have done is I have written it in the terms of Z plus 1 only. Right? So now I have already assumed that Z plus 1 is R e power I alpha. So what is Z plus 1 square? It is R square e power I 2 alpha minus 3 R e power I alpha plus 3. Right? So this becomes basically R square cos 2 alpha plus I sine 2 alpha minus 3R cos alpha plus I sine alpha plus 3. That is your Z square minus Z plus 1. Right? Now simplify this a little because we have to take the mod of this expression. So we can write it as R square cos 2 alpha minus 3R cos alpha plus 3 plus I common R square sine 2 alpha minus 3R sine alpha, right? Minus 3R sine alpha comes with the I here. This is your Z square minus Z plus 1 complex number. If I want to take Z square minus Z plus 1 whole square, I would have to say that is equal to R square cos 2 alpha minus 2R cos minus 3R cos alpha plus 3 whole square plus R square sine 2 alpha minus 3R sine alpha whole square, right? So evaluating this, you'll get R power 4 cos square 2 alpha plus 9R square cos square alpha plus 9 minus 6R cube cos 2 alpha cos alpha plus 6R square cos 2 alpha minus 18R cos alpha plus I will get a R power 4 sine square 2 alpha plus 9R square sine square alpha and a minus 6R cube sine 2 alpha sine alpha after expanding it, right? Now notice that this and this add up to R power 4. This and this add up to 9R square. I'll just simplify it and write it on top here itself. Right? So let's see what comes. Okay, so we are writing mod of Z square minus Z plus 1 whole square is equal to R power 4 plus 9R square. This and this are handled, this and this are handled, plus 9. And notice this is minus 6R cube cos 2 alpha cos alpha plus sin 2 alpha sin alpha, which is cos of alpha, using cos A minus B formula. And this is plus 6R square cos 2 alpha and minus 18R cos alpha. Right. So this is the expression that we are getting. And I want to show that this is greater than 1 by 4. That's my target. Right? So, okay. So I can write this as minus 6R cube plus 18R cos alpha plus this 6R square. Cos 2 alpha can be written as 2 cos square alpha minus 1. Right? And here I have R power 4 plus 9R square plus 9. Right? Now, if you think about this, I want to write it as a perfect square if possible. Okay? So let's see what we can do here. This part uh, I think I can write it as this is equal to 12 times r cos alpha minus r square plus 3 by 4 whole square plus 1 by 4 r square minus 3 whole square. Think about it. What is r square minus 3 whole square? It would be r power 4 plus 9 minus 6r square, right? So when you are writing it like this, you are writing it as 1 by 4 r power 4 plus 9 by 4 minus 3 by 2 r square, right? 6 by 4. This is what I am getting from the second term. And from the first term, what would I get? 12 r square cos 12 times r square cos square alpha plus 12 by 16 r square plus 3 whole square. 12 by 16 is actually equal to 3 by 4, right? R square plus 3 whole square minus 2 into 12, so 6 times r cos alpha into r square plus 3, right? And what you will get from here, 12 r square cos square alpha is present here. Notice this term is 12 r square cos square alpha, right? And if you simplify this, you will get r power 4 plus 9 plus 6 r square multiplied by 3 by 4. So what will be happening? 3 by 4 r power 4 will add up with the 1 by 4 r power 4. You will get an r power 4. 3 by 4 into 9 plus 9 by 4 will add up to 9. 9. And 3 by 4, so that is basically 18 by 4 r square. 9 by 2 r square minus 3 by 2 r square is 6 by 2 r square. So you're getting a 3 r square, right? Correct. So 3 r square you are getting from here, and more r square terms will come. You will be able to basically match this expression. I want you to do the calculations yourself. Like, it's just a little bit of algebra which you can do yourself and check. What I want to hint at here is that this is a sum of two perfect squares. This is a sum of two perfect squares. So this is going to be, this is greater than 0 plus, I know that r is greater than 2. So r square minus 3 would be greater than 1 by 4, right? This part is greater than 1. So you're getting whole thing is greater than 1 by 4, which means mod of z square minus z plus 1 whole square is greater than 1 by 4, which means mod of z square minus z plus 1 is greater than half. So what I'm saying is basically that this is greater than equal to 0 because it's a perfect square, and this part is greater than equal to 1 by 4. Right? So we are basically doing some algebra and we are simplifying it as a sum of two perfect squares. Okay, let's look at the next problem. This question says that let ABC be three complex numbers with modulus 1. Prove that mod of AB by A square minus B square plus mod of BC by B square minus C square plus mod of CA by C square minus A square is greater than equal to root 3. Okay, so ABC are three different complex numbers with modulus 1. So we can say A is equal to cos alpha plus I sin alpha. B is equal to cos beta plus I sin beta. And C is equal to cos gamma plus I sin gamma. Right? And then let's look at each modulus. AB by A square minus B square. If you divide by AB up and down, you get 1 by Divide a square by ab, you get a by b minus b by a, right? So this is basically 1 by modulus a by b minus b by a, which is equal to 1 by modulus a by b. What is a by b? It is cos of alpha minus beta plus I sine alpha minus beta minus what is b by a, which is cos of beta minus alpha plus I sine beta minus alpha, right? So now notice that cos of alpha minus beta and cos of beta minus alpha are equal because cos is an even function. So this gets cancelled like this. And you have I sine alpha minus beta minus I sine beta minus alpha, which gets added and becomes the same thing. So you're getting 1 by mod of 2i sine alpha minus beta. And mod of 2i is equal to 2 only. So this becomes 1 by 2 times mod of sine alpha minus beta, right? So the first bracket is becoming 1 by mod of 2 sine alpha minus beta. Similarly, you can prove the other brackets also. And what you end up getting is the left hand side is 1 by 2 mod of sine alpha minus beta plus 1 by 2 mod of sine beta minus gamma plus 1 by 2 mod of sine gamma minus alpha is greater than equal to root 3. This is what you have to prove. So you can take 2 on the other side. Basically, then you have to prove something like this, greater than equal to 2 root 3. This is what we need to prove, right? Now, at this stage, you should realize that each of these three quantities is positive because there is a modular sign. So we can apply AMGM inequality. We know that the sum of these three, we can say x1 plus x2 plus x3 by 3 will be greater than equal to cube root of x1, x2, x3. So basically x1 plus x2 plus x3 will be greater than equal to 3 times cube root of x1, x2, x3, right? And what is x1? x1 is this quantity, x2 is this quantity, and so on. So what we can say is that this LHS is clearly greater than equal to 3 times cube root of 1 by mod of sine alpha minus beta times 1 by mod of sine beta minus gamma times 1 by mod of sine gamma minus alpha, right? So LHS is greater than equal to 3 by cube root of product of sine of alpha minus beta, sine of beta minus gamma, and sine of gamma minus alpha, right? This is what we have proved so far. LHS is greater than equal to this quantity, right? Now let's think about the stuff inside the modulus. Sine of alpha minus beta, sine of beta minus gamma, and sine of gamma minus alpha. We can rewrite it as sine of alpha minus beta, sine of beta minus gamma, and the third one we can write it as sine of pi minus gamma minus alpha. This is the same thing as this term. Sine pi minus theta is equal to sine theta. And now if you think about it, I can write capital A as alpha minus beta, capital B as beta minus gamma, and capital C as pi minus gamma minus alpha. And you will realize that A plus B plus C is equal to alpha minus beta plus beta minus gamma plus pi minus gamma minus alpha. So what is this becoming? This gets cancelled. This is basically if you had just kept it gamma minus alpha, you would have gotten 0. Pi minus alpha plus alpha. So A plus B plus C, is it adding up to pi? Alpha minus beta plus beta minus gamma? Correct. So you have alpha minus gamma plus pi minus gamma plus alpha. You have pi plus. Okay, I wanted to rearrange this in such a way that we can end up with a pi. A plus b plus c is pi. Okay, so let's see if we have made some mistakes somewhere so that we can work it out. This is sine of gamma minus alpha. This is pi minus gamma plus alpha. If I say beta minus alpha here, gamma minus beta here, beta minus alpha, gamma minus beta, and pi minus gamma plus alpha. This will cancel. This will cancel. Oh, yes. So what you have to choose is reverse this sign, call this sign of minus sign beta minus alpha, and call this minus sign gamma minus beta, and keep it like this. So minus minus becomes positive, so this doesn't change anything. So what I'm going to say is A should be labeled as beta minus alpha, B should be labeled as gamma minus beta, and C should be pi minus gamma minus alpha. And in that case, what is A plus B plus C? In that case, A plus B plus C is coming out to be pi, right? Therefore, the LHS is basically equal to, this part is equal to mod of sine A, sine B, sine C, where A, B, C are angles of a triangle. A, B, C are angles of a triangle because the sum of the angles is equal to pi. Now, this is a very well-known inequality in triangles, that the product of sines, sine A, sine B, sine C in any triangle will always be less than equal to root 3 by 2 whole cube, with the equality happening in the case of equilateral triangles. So what we had was LHS was greater than equal to 3 by cube root of sine A, sine B, sine C, and that is equal to, now what we will do is we'll use this inequality here, the first inequality here, which is true for any triangle ABC, right? So if the product here is less than this, if I replace it with something less, okay, so we know that this is less than equal to cube root of root 3 by 2 whole cube, right? So obviously that means this is a larger quantity. So when I divide 3 by a larger quantity, it will be greater than equal to 3 by this, right? Should try to understand the logic. This part is less than this, so I'm replacing this with a bigger thing. When I replace it with a bigger thing, the inequality sign is preserved. It's greater than equal to. And what I get from here is basically 3 by, this is cube root of cube, so root 3 by 2. So 2 goes on top and this cancels and it becomes 2 root 3. So we have proved that LHS is greater than 2 root 3. So what are the things we used here? The question looked like a straightforward complex number question. We converted it into the Euler form. We wrote the inequality in terms of signs, and then we made a substitution. We used AMGM inequality first, and then we made a substitution to ensure that the angles are the angles of a triangle A, B, and C. And this is a well-known fact in a triangle. The product of signs is always going to be less than equal to this, with equality happening in the case of an equilateral triangle. That is what we have used to solve this particular problem, right? Okay, let's go on to the next problem. Right. So the next problem is this one. Let Z be a non-real complex number. Non-real complex number such that Z cube plus 1 is equal to 0. You have to evaluate evaluate what is z by z minus 1 to the power 2018 plus 1 by z minus 1 to the power 2018. So now z is a non-real complex number, so we can write this as a factorization. This is equal to z plus 1 into z square minus z plus 1. And since z is non-real, z cannot be equal to minus 1. Therefore, z square minus z plus 1 is equal to 0. Because the LHS was equal to 0. This is coming as equal to 0. From here we can see that z square is equal to z minus 1, right? And if z square is equal to z minus 1, I can replace this as z by z square to the power 2018 plus 1 by z square to the power 2018, right? So this becomes 1 by z power 2018 plus 1 by z power 4036, which becomes z power 4036, z power 2018 plus 1, right? This is my expression, and we know that z cube is equal to minus 1, right? Now, z power 2018 is basically z power 2018 is z cube the power 672 times z square. So this is minus 1 power 672 into z square. So it is z square, right? So this is simply z square. So what you will get is the top part z power 2018 plus 1 by z power 4036 is equal to z power 2018 plus 1 z power 2 into 2018, which is z square plus 1 by z square power 2. So that is z power 4. And how did I get this? Z power 2018 is z square because z cube is minus 1, right? And now what we can say here, this is z square plus 1 by z power 4, and z power 4 is equal to minus z because z cube is minus 1. So we write this as z square plus 1 by minus z. And we also know that z square minus z plus 1 is equal to 0. We had seen that earlier. So z square plus 1 is simply z, right? So therefore this is z by minus z, which is equal to minus 1. So our answer for this problem is minus 1, and the key steps involved were factorizing z cube plus 1 as z plus 1 times z square minus z plus 1. And after that, what we did was basically realize that z square minus z plus 1 is 0, means that z minus 1 is z square. We replaced that, did some algebra and simplified it. So hopefully you have understood how we are using the roots of unity in these problems. In the next video, we'll continue with the roots of unity, and we now apply it to polynomials. Like we'll apply it to polynomial questions. So slightly more advanced questions in the next video. Stay tuned for that, and I hope you'll learn much more from the next one. If you like the video, please subscribe to the channel and share this with your friends. Hopefully they will also benefit from the course here. I'll see you next time.